So very good day to everybody. Once again, this is using Python in multimedia and gaming machines, and in today's class, we'll understand the basic audio compression about the adaptive delta pulse code modulation. So this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again, let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students, and young researchers. Right. So we will understand the basics of audio compression, how you will explain with the audio compression, how do you define the attack time and then release time. Okay, what is the definition of this? The output gain, the optical compressions. Then we will have VCA. Okay, so that we will be explaining about the digitization of signals, adaptive differential pulse code modulation, ADPCM. Okay, about its block diagram, difference between this DPCM, okay, and ADPCM. So that we'll be discussing about the advantages and of course the disadvantages. Okay, so I've already given the independent work in MS. Please complete them as soon as possible, and at regular intervals I'll be giving you some short videos to discuss the knowledge in our topics. Right. So whenever you say like audio compression, like you have like compressors or automobile limiters, so that you will be using as the music production tools that is going to reduce the span between the softest and of course the loudest parts of the audio signal. So you can control the levels. Okay, when used properly, you can result in much more louder and more professional sound recording. Okay, so maybe even the audio software that you can use, especially for recording the signal set, you can boom the quality level. Okay, so compressors, using compressor you can understand how you can get the recordings that you are going to have a professional and a radio ready format. Okay, so when used properly, you can make use of your tracks. Okay, the sound more punchy, even balanced. Okay, and of course loud enough. Also you are going to inject the coloration and tone, so it will be very much quality enough. But over compressing can actually squeeze the life out of your recording, so that also happens. So having a good grasp of the basics, then definitely you can understand the importance of using the tool. Okay, so whether you are using a hardware compressor or maybe a plugin, okay, additional plugin, so there are a few common controls that you should be familiar with. For example, threshold. It's the level at which the compression effect is actually engaged. So if the threshold limit is set at like minus 10 decibel, so only signal peaks that extend above that level will be compressed. For example, if you take in the case of OBS Studio, open broadcast software, so that also the threshold limit is actually maintained. So you can set that. So above that, if you set means, then it will be too much of noisy. Okay, maybe below that you cannot maintain that accurate quality level. Okay. Then you have knee. Okay, so knee refers to how the compressor transitions between the non-compressed and of course the compressed state. So here most compressors will be allowing you to choose between hard knee and then soft knee. Okay, so some compressors you can actually select positions between the two types, like hard knee and then soft knee. Okay, so this is the soft knee, okay, like a hard knee. Okay, so this is the threshold limit, and this is the input level in decibel and output level versus in decibel. Okay, so here the soft knee will be allowing for smoother and more gradual compression than the hard knee. Okay, so that is the thing. Then you have attack time. So it's a time taken for the signal to become fully compressed after exceeding the threshold. So which means that if you have faster attack times, like we will be having 20 to 800 microseconds, slower attack time will be like 10 to 100 milliseconds. Okay, so some compressors will be expressing this as the slopes in decibel per second rather than time. Okay, then you have release time. So it's opposite of the attack time. So it's the time taken for the signal to go from the compressed state back to the original non-compressed state. Okay, so release times will be longer than the attack times. So generally it might be like 40 to 60 kirit than altamish milliseconds to maybe like ikka than bish seconds. Okay, so that much it will be larger than the attack time. So like the attack time, so you can express it as the slopes in decibel per second. Okay, so this is the input signal. Okay, so that we will be measuring in the threshold. Compressor gain. Okay, so we will be having attack time and then release time. So here the attack time it reduces, becomes stable, and then it increases. The output signal will be having like ripples. So here it's normal, and after that it's increasing. Okay, then after that it becomes normal. Okay, so this is attack time and then release time. So this is the ratio. So with regards to compression, we specify the ratio. So it's nothing but the amount of compression that is actually applied to the signal. So settings you can express it in the dB, decibel format. So for example, 2:1 ratio indicates that the signal is exceeding the threshold by 2 decibel will be actually attenuated down by 1 decibel. So the signal which is exceeding the threshold by 8 decibel will be attenuated down by 4 decibel. Okay, so here we'll be having like 1:1 ratio. So that represents a unity gain. Okay, so in other words, it will be unity gain means attenuation york. Okay, so maybe if you have 3:1, which means moderate compression, and 5:1 will be medium compression. 8:1 strong compression, 20:1 or maybe like infinity:1 would be limiting factor. So that will be an effect to ensure that the signal essentially never exceeds a set threshold. Okay, so maybe if you have input level and output level, so this is with the regards to threshold. Okay, 1:1 this one, 2:1 this one, 4:1 this one, maybe here 8:1. Okay, up to infinity:1. So that is the limiting factor that is not exceeding the threshold limit. Then you have the output gain. So although we try to understand the compressed signals as being much more louder, so compression results in overall lower output. Okay, so this is where the output gain or maybe the makeup gain comes into practice. Okay, so here the output gain is going to make up for the attenuation which is actually achieved by the compressor. So some compressors will be providing meters to visually indicate the total attenuation in decibel, so that you can have a correct estimate of the makeup gain. So maybe if you take here, okay, like we will be having adaptive differential pulse code modulation input. So that is being passed on to the FF. Okay, fast Fourier inverse adaptive quantizer. Okay, so maybe it will go for bit masking, FP inverse adaptive quantizer. Okay, so everything gets added up, okay, to the adaptive predictor, okay, to produce the PCM up. Okay. So hardware compressors maybe either will be using tube type or be solid state components, okay, from the output gain stage that can influence the amount of color and of course the character applied to your track. Okay, so these are the common compressor types. We have tube type. Okay, so back during 1950, okay, so maybe for color, for warmth, harmonics, so you use the tube. Okay, so they will be having slow attack and slow release time. So that is how you will have that old sound. Okay, so that can be difficult to achieve with other compressor types. So this is actually tube type. Okay, then you have optical compressor. So optical compressor will be having a light. Okay, so a light element and a optical cell. Okay, so here you can actually adjust. So when the amplitude of the signal is going to increase, so here the light element will be emitting more light, so that will be causing the optical cell to attenuate the amplitude of the output signal. So this is what you get with the optical compressor. Then you have FET, field effect transistor. So that will be emulating the or having the tube sound. Okay, but you can use it with the transistor circuits. Okay, so they are very fast, very clean, and of course much more reliable, especially for punching up the drums, vocals, bass, guitar, so that you can use the FET type. And VCA, okay, so that is voltage control amplifier compressors. Okay, so fast and punchy VCA compressors you can have to run the gamut. Okay, so from the Rolls-Royce compression of the SSL G bus or maybe E, okay, to the hot rod attitude of the legendary that bass effect like 160. So this category can add under-lengthening character maybe for the drums, guitar, and mixed bus you can have. Okay, voltage control amplifier. And then you have adaptive differential pulse code modulation. So that's what you call to be the DPCM, delta pulse code modulation. So for the signal, it's a compression coding, okay, using different differential values like maybe differential pulse code modulation. Okay, so where the quantization stages scaling is adapted additionally based on the signal curve. Okay, so this one you will be based on the standards of the International Telecommunication Union T standard, okay, like the G726 in the audio signal. So maybe in these applications, the data rate of the output can be adjusted along 16 kilobit per second and maybe 64 kilobit per second. Okay. So this is another example, okay, like DECT, Digital Enhanced Cordless Telecommunication. So maybe for the cordless telephone, you pick it up and you speak, okay. So for this one, you will be using signal performance in the past, and of course you are going to predict in the future, okay. And the output signal will actually signify the prediction error, which has no importance. So the signal should be decoded in order to restore a very strong and original signal. So the main function of ADPCM is how you try to transmit the sound signals with the help of fiber optic long distance lines. So this modulation is very helpful, especially for arranging the digital lines among remote sites for transmitting both voice as well as your data. Okay. So before they are transmitted, the voice signals are actually digitized. Okay. So this ADPCM method is actually used in the telecommunication field for compression of speech signal, because it will actually reduce the flow of bit without reducing the quality. Okay, so you can use it in waveforms, images, and especially audio with high quality, and data in the other modern techniques as well. So the operating principle, okay, so ADPCM is actually like PCM, pulse code modulation, using the prediction function. So when the signal is actually processed and the effort is actually made to focus the additional path of the signal in the next segment. So for the signal quantization within the next time step, okay, only the disparity that is actually predicted, so that the real signal can be actually used. Okay. So because of this, different configuration that we are using, so the small amount of bits can be utilized to actually explain the signal. So using this technique, okay, both the quantization level and of course the prediction function are actually adapted for every work step. So when you compare with the DPCM, digital pulse code modulation, you will be having an enhanced signal prediction. So here you can use it for emulating the computers, or maybe like arcade games you can use them. Okay. Then you will have the block diagram. So we'll have the characteristics for adaptation of 64 kbps ALA or maybe MULA PCM channels from a 16 kbps channel, or maybe 24 kbps, 32 kbps, 40 kbps, you can use them. Okay. So the adaptation can be applied to the PCM pulse code modulation bit stream through the ADPCM transcoding method. Okay. Right. So the main relationship between among the voice frequency signal as well as encoding decoding loss is completely specific of this G711 standard. Okay. So maybe you can apply this 24 kbps or maybe 16 kbps for the voice within the digital circuit equipment. Okay. So maybe the 40 kbps you can use it for holding the signals of the data modem, okay, in the digital circuit equipment as well. So especially for the models, maybe for the modems which operate above 4800 kbps, you can use them. Okay, so just this ADPCM, adaptive differential pulse code modulation, it's actually simplified like the encoder and decoder what we see over here. Okay, so here we will be having linear input sample 812 bits, so that is passed to the different signal, the encoder. Then we'll go with the step size, okay, Z inverse, then step size calculation. Okay, here we'll be calculating the estimate of the last input sample. Okay, so here also Z inverse, here encoder, here decoder, so everything it's being, okay, clubbed up, okay, for the ADPCM output sample bits. Okay. So here the encoder, here will be employing the last MULA and then ALA. Okay, so the input signal of the PCM to the consistent PCM will be having the disparity signal being acquired through subtracting the approximation of the input signal from the input signal itself. Okay, so here you will be using adaptive signal maybe 7, 15, 31. So otherwise you can use a 4-level quantizer. You can assign it for the 5, 4, 3, 2 binary digits corresponding to the different signal value what we saw in that diagram. Okay, so here we'll be using inverse quantizer, so that will be generating the quantized dissimilarity signal, okay, using the binary digits. So here the estimation of the signal can be actually added towards this quantized difference signal for generating the reconstructed edition of the input signal. Okay, so both the signals may be like quantized difference or may be reconstructed are actually function, okay, through the adaptive predictor. So that gives the estimation of the input signal where you try to generate the feedback loop. Okay. Then after encoding, you will have decoding, so that you are going to reconstruct the original signal. Okay, so it is going to use a identical structure through the feedback part of the encoder, okay, as one through the consistent pulse code modulation towards the conversion of the A log or maybe mu log and an adjustment of the synchronous encoding. Okay, so the adjustment of the synchronous coding will be stopping the increasing distortion which is actually happening on the synchronous stand-up, maybe like pulse code modulation or maybe adaptive differential pulse code modulation under some specific conditions. So this synchronous coding you are going to adjust, okay, by adjusting the output codes of the pulse code modulation, okay, so, such that you will have to remove the quantizing distortion within the adaptive differential pulse code modulation encoding phase. Okay. So this is the difference between DPCM and ADPCM. So DPCM, it's delta pulse code modulation. So here you'll be using multi-bit disparity value. Okay, so that can be actually stored. So here you can use bipolar D to A, digital to analog converter, especially for playback to change the consecutive disparity values towards the analog waveform. And ADPCM, it's actually adaptive delta pulse code modulation. So here the disparity value can be regulated mathematically based on the input waveform slope. So that is actually stored. Okay. So here also like bipolar digital to analog converter can be used to change the digital code, which is actually stored to analog, specially intended for the playback. Okay. So these are the advantages of ADPCM. So the modulator doesn't actually follow the input signal for a very long time in the delta modulation. So once a change within the signal is actually little, as well as the modulator will be overworking. So once the signal slope is actually very high. So the delta pulse code modulation problems are actually eliminated through the ADPCM, adaptive delta pulse code modulation. So based on the signal variation, the step size will be particularly changed, and the compression of the bandwidth is one such benefit of ADPCM. Okay, because a single wire is actually utilized for transmission in place of the what we employ with the digital communication system. Even it uses low power for the transmission of bits, and you can reduce the synchronization problem also, because there is no requirement for start or maybe stop bits for handshaking. Okay, so it's much more easier to implement also. Okay. So you can also use it for obtaining the financial and of course proficient digital coding for speech, okay, through the bit rate for the range of 24 kbps to 32 kbps. Okay. But the disadvantages, like the receiver should be capable to adjust the step sizes, okay, within the same method as the transmitter. So the quantization noise, okay, is how you will have like no errors. Okay, so this is actually a problem. Quantization noise is a problem. Then the continuous variable slope delta modulation CVSDM will be having the extension or maybe development over the ADPC.